Okay, guys. After a review about the linear node training, that is a little bit faster than the first version that you have seen on the clip. I'd like to go to the sigmoid node. So the idea of the sigmoid node is quite simple. We have the summation unit, right? And we must have the output, but the output will be activated but not using the threshold like the threshold TL and the threshold linear neuron. But this time we use the sigmoid one, and the sigmoid is the function that we already studied, and we've seen the behavior of the sigmoid unit. So let's see something here. When you have the output, when you have the input from other nodes, we have W0 and X0 to be 1, right? We have W1 for X1, we have W2 for X2, and we have Wn for Xn. So the summation is W dot X, or summation for all I, Wixi. This is a summation, and you have to send these values to this activation function. The activation function of the sigmoid is quite simple. This is the sigmoid function of any input will be 1 by 1 plus e power minus y. This one is a sigmoid function, very important function. And you have known that the values of the sigmoid must be greater than 0 and less than 1, and not equal to 0 and 1. Okay, so that's all. And if the input y is negative, it is it is close to 0. But if it's greater than 0, it must be like close to 1. So this graph will be, it should be something like this. It will pass the input. When input is 0, the output is 0.5, and it will be greater than 0 and less than 1. This is the sigmoid. And you can see that we can use this sigmoid function instead of the threshold linear neuron, because the threshold linear neuron also give this output to be 0 and 1, but the threshold linear is quite sharp here, right? It used this part, the comparison. If it's greater than 0, it will be 1. If it's not, otherwise, it is 0. So now the idea is you can use the sigmoid instead of the threshold linear neuron. And guys, we have one thing of the sigmoid function. The sigmoid function is a nice function that the derivative of this function by itself, differentiation of this function, the sigmoid function by dy. It is, look at this. This is by dy of 1 by e power minus y. So I will move it up to here, but power minus 1. So it is like diff of u minus 1. So it is minus 1 u power minus 2, right? And du by dy, right? So we will use this the differentiation, this equation, very easy, right? It is the same way that you did several times. So now this time it will be minus 1 of okay power 2 and diff of dy1 by here. Oh, sorry, not 2, it minus 2. Okay, so it will be power minus 2 and 1 is constant, and this one e power y by dy, it must be minus 1 right, right. So it is and this one minus and minus, so it becomes um, so it is right, right. So this one is the sigmoid itself, right? And this one is, so I will change this one to sigmoid. And this one is uh, is it true? Is it true? Right? So it is same, right? So it will be sigmoid of y. This one is 1, right? So it will be 1 minus, and this one is the sigmoid y. So the differentiation of the sigmoid of y will be the sigmoid itself times 1 minus sigmoid itself. This one is very, very nice property. And we will use this one. We'll use these values to find the equation that we can use to train the sigmoid one.